Hello everybody, I'm Abhinaya from Team Laila. Today we are going to give brief overview on color models. Color models is very interesting and very happy topic. I'm gonna recollect all your school subjects like physics and biology. These are the topics covered by my team. So let's get started. So first of all, I would like to give brief overview on where we are using colors even in our day-to-day life. So, if you observe this traffic signal, we use red, green, and yellow colors. So, here color is used as communication medium to help safe journey for the people. Red light has long wavelength and it is visible from far distances. In electromagnetic spectrum, next to red, we have yellow with greater wavelength and then green color. Hence, we use these three colors to make our journey smooth. Coming to the next scenario, let's have a look at fast food center icons. Can you guys observe the similarities in these three icons? The similarity is all these icons have red color in common. According to the color psychology, red color causes to feel hungry. Hence, color is used as marketing factor to improve the sales. So now coming to our own field, computer science engineering. Just observe the web page shown on left side. It is so clumsy, used very bright colors to display the web page, which is less readable to the users, whereas the right web page located in right side, saturated hues and good color combination used on the right side web page, so which is more readable. Hence, color plays vital role in our day-to-day life. So I'm going to discuss few basic concepts like what is color, what is light, and how color is produced from light, and the color properties like saturation, hue, and brightness. So basically, color is a property of light, and light comes from light sources. So how human eye perceive the color whenever light fall on any object, the color ray is perceived by human eye. So when you see a red pear here, the red fruit, so whenever white light fall on the red fruit, so it absorbs all other colors into that object and reflects only red color. That's why human eye is able to see the red color. So when you go into very detailed way, so the human eye will have retina, and retina consists of multiple cones. So these cones will absorb only blue, green, and red colors. So let's say we are observing green leaf. Now leaf sends color waves to retina and the cone absorb green and intimates to the brain that it is in green color. So how do we define the color? Color has many definitions. In physics, the color is defined as the frequency of radiation determines the color of light, and again, the color is a very narrow spectrum located in electromagnetic spectrum. We are going to see how it is in next slide. And in biology, we have another definition that it is a excitation of photosensitive molecules in the eye, and it is interpreted by the brain. So we'll see all these definitions in coming slides. So this is electromagnetic spectrum. So this electromagnetic spectrum consisting of seven radio waves, electromagnetic waves. So in this visible light is a very narrow frequency band. So you can observe in the below. So this color visible spectrum is consisting of seven colors. So this spectrum is called visible light spectrum. So this is very detailed diagram of visible light spectrum which starts from 400 nanometer wavelength to 700 long wavelength. So violet color has a shorter wavelength and red color has long wavelength in a visible spectrum. So in biology, this is a human eye. So whenever color light fall on lens, so it directly goes to the retina, and retina consisting of two properties. one is rod and one more is cone. So cone is a very small cell. We have 5 to 6 million cones, and these cones will absorb only red, green and blue colors. And then we have rods in our retina. So these rods are useful when we are in a dim light, if we want to observe each and everything under dim light. So rods will help us to perceive the things in dim light. So do you guys guess how many colors human eye can identify? So I have a count of colors here. So human eye can distinguish 128 different colors or hues, and then in each and every color we can again distinguish 20 different shades and 130 different tints. So I'm going to explain what is shade, what is tint in the further slides. So approximately 380,000 colors human eye can perceive. Coming to the characteristics of colors, you can observe this diagram. So we have three properties of color: hue, saturation and luminance. Hue is nothing but the color. The color is distinguished again by using different wavelengths. So the second property is the saturation. So when you take the normal color and add gray color into that color, so it gives the saturation. And coming to the third property, luminance. So when you add white color or black color to any particular color, it gives the luminance. And color is measured by using chromaticity. So chromaticity is a measure which uses basically purity and dominant frequency to measure any color. So let's have a look at one small experiment. We can do it at our homes. Take a piece of white sheet and place it under the sun. So you can observe this white sheet as a pure bright white sheet, but the same sheet if you place it next to two candles in dim light, so you can observe little bit reddish combination of light. So where does this red color came from? So Newton, in history, Newton has done one experiment that he placed one prism under the sunlight, and he observed that white light is a combination of seven different colors. So, after Newton's experiment, so many scientists have done furthermore experiments and then identified that each and every color will have different color wavelength. So, the wavelength is distinguished by different colors. Say, for example, blue color is having very less wavelength, and then red color is having greater wavelength. So, these are the experiments done after Newton. So now coming to the properties of light, we have three major properties of light: frequency, wavelength and period. So coming to the frequency, frequency is the number of waves that pass at one particular point for any particular time frame. So you can observe the diagram below. So the wave is defined below. So when you just take the lambda is nothing but the wavelength. So wavelength is a distance which the wave shape repeats. So, the speed of light can be calculated by using frequency and wavelength as shown in the equation, and the period is 1 by frequency. So, that is the time taken to complete one complete cycle of the wave is defined as period. So, these are the three properties of light. Color also produces energy. So when you observe this graph, white light produces more energy than brown. So in along with energy, color is also defined as wavelength. So that's why when you just place a car in a parking lot under sunlight, and again once you back from couple of minutes, you can observe that car is so hot inside. That means from white light the object will produce energy as well. And to summarize my topic, when you place a white object under sun, it emits the entire white light. So it's not going to absorb any kind of light. That's why it's visible in white color. So when you place a black color under the sunlight, so it will absorb all the white rays, including red, green, blue colors into it. That's why we can see that object is colored in black color, but when you place a red shirt with blue pants under the white light, so you can see that it absorbs all other remaining colors, yellow, green, violet, and then it's going to produce only red and blue color. That's why we are able to see this. So this is a summary of properties of light. So energy distribution of white light. So as I said earlier, Newton has placed prism under the sunlight. So white light is a combination of all other seven colors, and this white light is produced by white light sources like natural sources, stars and sun, and artificial sources like LED bulbs. So you can see the diagram here. So white light is distributed into multiple colors with variated energy, and in this energy you can see that in between red and violet, one color is having more energy than all other colors. So this is called dominant frequency here. And I'm going to tell the basic definitions which we use in color models, that is color wheel. So color wheel is in form of circle which have all combinations of colors here. So I would like to tell you what is primary colors and secondary colors. Primary colors are the sources of colors. So by combining these primary colors, we can produce secondary colors and tertiary colors. Primary colors are blue, red, and yellow here, and green, orange, and purple is called secondary colors. We have two color models: additive color model and subtractive color models. Additive color model is a combination of red, green, blue. So if you take a black screen and then just place red and green, the combination of red and green gives yellow, the combination of red blue gives magenta, and the combination of green and blue gives cyan color, and combination of red green blue together gives white color. So this concept is used in multiple display systems like LED TVs and your laptop screens and digital cameras. So when you just observe the screen closely, you can see pixels. Those are in red, green, and blue. So by using this additive color model, so when we combine any two colors, it is going to produce new other color. So pixel in digital media is going to fool the eye into seeing all the colors using only red, green, and blue. And when you coming to the second concept is subtractive color, just take a white sheet and subtract all other colors. See, if you just subtract red from the white screen, you are going to get green and blue, so which is cyan color. So likewise, we have multiple color combinations which is absorbed by green, blue, and it is going to produce magenta and yellow. When you just subtract all the colors from the white screen, then we'll get black color. So this concept is used in printing technologies. So printing presses uses CMY cartridges. So this is a diagram for cartridge, and including CMY we use K also. K is nothing but a key. So black color is defined as a key. So why we are using key instead of black color B? So because blue is already defined as B alphabet. So to reduce that complexity, we are using K to define black color here. So CMY is used in printing, press printing, newspapers, any printing devices. Color mixing is used by so many artists while drawing any diagrams. So they use three concepts: tint, shade, and tone. Tint is nothing but when you add white color to the color, any particular color, it is going to give the tints. When you add black color to any color, it is going to give the shade. But when you add both white and black together, it's going to give the tone. So these are the three concepts used by artists while drawing any picture. So color mixing, again we can see here RGB, CMY, and RVB. So when we mix any two colors, we will get different new color. And color mixing, when you observe this color wheel, you on one half you can see all cool colors like very pleasant colors, but when you observe on the other hand, it's going to give all warm colors and bright colors. So this is the beauty of color wheel. And when you want to choose any two different colors from the color schemes, you are going to use six different color schemes here. First one is complementary color. So when you just want something to stand out, then you can choose two complementary colors which are located on opposite side of the wheel. But when you want to use pleasant pleasing color combination, you can go for analogous color scheme. So when you just take three colors on three sides like the triangle, so when you want more vibrant combination of picture, then you can go for triad color scheme. So split complementary is little bit different than complementary color scheme, so where you are going to choose two analogous colors and one complementary color to combine split complementary color scheme. And you can also choose rectangular color scheme and square color scheme for plenty of variations in the color combinations. So, can you guys just observe this image and just tell us where the killer is hiding? I'm going to give you 5 seconds. So, here the killer is hiding. So, the main drawback of this picture is they are using analogous color scheme to differentiate both the objects. So, that is the major drawback of this color picture. So, we can use different color schemes to stand out few different objects. Again, when you observe these four pictures, you can't really see what the number is inside. On the right hand side, you can clearly see 12 and 42 are inside the circle, but left side, if you see, the color contrast is almost similar, and they are not using contrast colors. That's why you are not able to see 29 and 15 numbers very closely. And again, this is one more picture that when you just observe the waves of water, so you can see each and every detailed portion in the left hand side gray color picture. But if you use different colors like green, yellow, and combination of orange, so you can't see the minute details of the picture. The originality of picture is lost by the color combination. And by combining three different colors, red, green, and blue, we are going to get any numeric value for any different combinations. So if you want yellow color, so you can use these three parameters by using matching function. And then if red value is something, green value is something, and blue is something, so we are going to get other different colors by using the color matching function. So this is a CIE color model. So it's this is an experiment conducted by two scientists in 1931. So the experiment is shown here. So the human eye is able to see three color combinations in one screen, and the new color is going to display on the other screen. So they have conducted this experiment for several multiple times and provided one mathematical value for each and every new color generated by RGB. So once they get all the values for all different colors, they have drawn a graph, and they are able to see this particular shape of closed human visible spectrum. So this human visible spectrum is as in a horseshoe shape. So this is the final color horseshoe shape visible spectrum where we can define multiple colors in a single graph. Thank you.
Okay, let's talk about the chromaticity diagram. Basically, the term chromaticity refers to the quality of color independent of brightness. Okay, so the chromaticity diagram is an objective specification of the quality of colors independent of the luminance of the colors. This chromaticity diagram consists of two parameters. The first parameter is the hue, the H. Basically, this is about the color appearance of a color, which is defined technically as the degree to which the stimulus of any given color, how far is it, or close to the stimulus of three colors, green, blue, and yellow. So in the picture shown below, there is an example of the chromaticity diagram of the HSB and HSL. Basically, these two chromaticity models, for example, the HSL represent the hue, saturation, and lightness, and HSV presents the hue, saturation, and value. Those are alternative representations of the RGB color model that were designed in the 1970s by computer graphic researchers. These two example models were introduced in order to more closely align with the way the human vision perceives color making attributes. Okay. Okay, let's talk about the history of the chromatic diagrams. Okay, the chromatic diagram was introduced by CIE, which is the Commission Internationale de l'Éclairage, or the English version of the name is the International Commission on Illumination. It was founded on 1913. Okay, one of the earliest chromatic diagrams was the CIE RGB, which was introduced in 1920 by David Wright and John Guild. So these two persons independently conducted a bunch of experiments on human sites, and then they tried to determine the colors that human eye can perceive, and then give it mathematical basis. Then what came after was the CIE XYZ. So based on the result that these two people that I just mentioned gotten for the CIE RGB version of the human eye, the CIE mathematically determined a color space, okay, called the CIE XYZ in 1931 color space. If you don't really know what is the color space is also known as the color model or the color system, which is basically an abstract mathematical model that simply describes the range of colors as tuples of numbers, typically as 3 or 4 values or color components. For example, the RGB, 3 color components. Generally speaking, the color space is an elaboration of the coordinate system and subspace. Each color in the system is represented by a single dot. But be careful, the XYZ here does not really refer to the RGB. X, Y, and Z parameters are extrapolations of the RGB created mathematically to avoid the negative numbers, okay? And then they are called the tree stimulus values. The Z somehow is equivalent to the blue color value. X is a mixture of the cone response curves that was chosen to be orthogonal by luminance and non-negative. Then now, a slightly adjusted version of the previous model chromaticity diagram is the CIE XYI. In this model, Y represent the luminance, the uppercase Y, and the lowercase x and y presents the chrominance values derived from the three stimulus values x, y, and z that were described in previous chromaticity diagram, in the previous version of this diagram. Then followed by the CIE lab. This lab actually is a combination of three parameters, L, A, and B. In different words, this is a combination of color model and the space combo, where the parameter L reflect the brightness, and A and B are just chrominance components. Okay, the relationship between chromaticity diagram CIE lowercase xy and all uppercase xyz. So we can there is a concept called normalization, where we can derive the chromatic diagram lowercase xy from the uppercase xyz. So on the right hand side, you just see simple mathematical formulas. We call them normalization formulas to derive the chromatic diagram parameters x, y, and z. Okay. Again, on the upper corner, you see the same formulas that I just showed in the previous slide on how to derive x, y, and z for the model CIE lowercase xy from the CIE uppercase xyz. And then at the bottom, you see formulas on a general case of formulas to derive the uppercase xyz for the chromatic diagram CIE uppercase xyz. So we have two cases. We have two formulas here. One on the right hand side, which is for the when we have reflective and transmissive case, and the one on the left hand side is for the emissive case. Okay, these two formulas involve some physics formulas and some physics components like lambda, the gamma ray variable, and so on and so forth. Nowadays, there have been so many applications for chromaticity diagram, okay, such as color names for lights. Basically, here the chromaticity diagram can serve as a kind of color name map for lights. Okay, we basically try to name different types of light colors based on the current colors we have. And also there is another application called additive complementary color pairs, which is basically about using the chromaticity diagram to serve as a type of color circle for identifying additive complementary color pair. I would introduce the complementary color concept in later slides. And there are so many other applications, such as the metameters, the color temperature, the color limit for materials. What are the displayable colors in the chromaticity diagram? Basically, the displayable colors is that when you combine two colors, give you the third color. Okay, so for example, the purple color has two values. Okay, the first value from the red comes from the red color, and the second from the green color. For example, if you compare the value of 85 from green and 246 from red, that give you the purple. Okay, so the displayable colors, again, when you combine two colors in the chromatic diagram or multiple colors, give you another color, a completely different color. Okay. But then we have the complementary colors that I just mentioned. The complementary colors are very different in concept than the displayable colors. Basically, in complementary colors, when you combine two colors, one of them would be canceled out, or they could both cancel each other out. This means, for example, when they are combined, they produce grayscale color, like white. The formula to calculate the purity is too simple. It's on the right-hand side. The parameters involved are D for density. The A and B should be for, that is, the A is for the green and red combination, which is the color purity, blue and yellow color component combination. The color purity is somehow equivalent to the term saturation in the HSV, the hue, the dominant wavelength, color purity. Basically, the dominant saturation, we get it by drawing a line from measurement of the purity of the color, the white color, and the purity of the color basically reflects how much, and then you draw this given color all the way to hit the wavelength by the white color, the wavelength. So on the figure you see on the left-hand side, whatever the intersection, you try to dilute value should be the red color with white. When the saturation has. Let's talk about the RGB color model. Before we talk about the RGB color model, let's introduce some concept and principle of about the theory of colors. So the principle here is that any color spectra is perceived by sensors with three different response frequencies. Okay, and also the color should be inherently presented in three-dimensional space. So how to describe the color spectra numerically? And before, we need to figure out why do we exactly need only three colors to represent any other given color? Why can be 4, 5, 6, or any bigger number? Basically, here it's more about optimization problem. If we can generate the same color using only three colors, why do we need to bother to generate the same color using more than three? Okay. So any color spectra is perceived as has three parameters: the hue, which is basically about the single dominant wavelength, and also involves the saturation, which is about the mixture with a certain amount of white light that I just explained earlier. And another parameter is the intensity or the brightness of the color. So again, the RGB color model is too simple. Any color is represented by a combination of three main colors: red, green, and blue. And here is the RGB color model. This is the color cube for the RGB color model. So this cube, so the coordinates in this cube of each point in the cube are used to find the color on the RGB, red, green, and blue scale. For example, on the corner point with the coordinates 0, 0, 1, that should be the blue color. The red value is 0, the green value is 0, and the blue value is 255, which gives the blue color. This table shows example or samples of colors generated based on the primary colors red, green, and blue. For example, the black is combination of red, green, and blue that all where these three colors have 0 values. Okay, so basically the black here is combination of no color. The color gamut. So as you might know, each device might have a different color range. For example, the laptops should be different than classroom projectors, different than phones, printers, and so on and so forth. So since each device can reproduces its own range of colors, we need to define the gamut of the color for this particular device in order to understand the way this device reproduces the colors. So this is an example of color gamut for a typical RGB computer monitor. Okay, so in this chromatic diagram, you see the range of all possible colors that this monitor can reproduce. Again, in terms of red, green, and blue. The YIQ color model. I believe this color model was first introduced in the United States for commercial color television broadcasting in TSC. And the idea here is simple. This color model is just a rotation of the RGB color space, such that the I axis represents the combination of orange, blue, and the Q presents the combination of purple and green. And the reason for this arrangement is that the human visual system is much more sensitive to changes in the I axis than the Q axis. And also one more reason for this rotative color model is that it conserves the bandwidth, because early in the 1970s, when we had color and white TVs, right? So people had to come up with this color model in order to conserve the bandwidth and also to transmit with less fidelity as well. In this last slide, I just show how to convert from the YIQ color model to the RGB color model, or the opposite, from the RGB color model to the YIQ model. So I believe nowadays we have many softwares that can do the conversion automatically, so we don't need to do any calculation by hand. But this is just simple. Just if you are interested in knowing how to do it by hand, for example, you just write down the values of each component in the YIQ model, and remember each color is represented by 3 values. Okay, then you just put the YIQ values for each single component, and then multiply them by the RGB, the values for the red, green, and blue, and then you get the YIQ equivalent of that particular color, and vice versa. In order to convert the YIQ to the RGB, then you just multiply the values of RGB colors by the YIQ, and then you get the equivalent color on the RGB scale model or color space. And thank you.
Hi, this is Hemnath, and I'm going to continue this presentation from the topic CMY color model. So before that, why do we need a CMY color model? To answer this question, the things we are doing in a digital monitor, we are able to see the colors. That is mainly due to the process of addition of colors. So when you try to get those things being printed in a paper, you need to have something called CMY color model. It does the process of subtraction of colors from the white light. So in the CMY stands for cyan, magenta, and yellow. These are also called as complementary colors, but are called as subtractive complementary colors, which can be obtained from mixing the primary colors called RGB. So it is used for hard copy devices. In contrast to the color on the monitor, the color on the printing acts as a subtractive, not additive. So what do you mean by subtractive color? As I said before, it is a process of subtracting the color from the white so that the left out color is being displayed by the white light, which your eyes can catch it. So let's see the relation between the CMY and RGB color models. So on the left side of the image, you can see the RGB Venn diagram. In this, you can see that when you mix all the three, red, green, and blue, you can get a white light. So in the absence of red, green, and blue, you will see the dark outside. So when you mix red and green, you'll get yellow. When you mix green and blue, you'll get cyan. When you mix red and blue, you'll get magenta. Similarly, on the other hand, you have the CMY Venn diagram. In this, you can see that in the presence of cyan, magenta, and yellow, you'll get a black color. In the absence of cyan, magenta, and yellow, you'll get a white color. So which means that in the white light, if you are separating cyan, magenta, and yellow, then you have nothing. So it's used to display in a black color. So if you don't have anything, then you have the white color. So you can see that by mixing magenta and yellow, you are getting red. This is because of the process. Like back in the RGB Venn diagram, you'll get magenta when you mix red and green, red and blue, which means that magenta component consists of red and blue, but it does not consist of green. So when a white light falls on a magenta, it absorbs the green while reflects the red and blue. Similarly for yellow, the blue gets absorbed and while the red and green gets reflected. So when you add yellow and magenta together, the magenta will absorb green, the yellow will absorb blue, so the red light gets reflected. That's why that's red in between. The similar thing holds for green and blue. So to understand that in a very detailed manner, you can see that when a white light falls on this red pigment, you see that red is being reflected while green and blue being absorbed. Similarly for green and blue. So when you see this in the CMY model, the cyan component consists of green and blue. When white light falls on it, you can see that the green and blue getting reflected while the red is being absorbed. To demonstrate this, I have experiment which is being displayed in this GIF image. You can see that when you turn on the red, green, and blue bulbs, when you put a screen in front of it, you can see the white light coming due to the addition of RGB colors. So when you put an object, an obstacle in front of it, all the three lights create its own shadows, which means that the shadow created by the red color, it means that the red light cannot reach that place, but the blue and green can fill that shadow. So when the blue and green mixes together, you can see that a cyan is being filled in the shadow created by the red. So let's talk about the conversion to RGB. In this equation, it is mentioned that red can be obtained by subtracting cyan from 1. In this case, you consider white light to be 1, and you know that cyan component consists of green and blue. So when you subtract it from the white light, you will get the red. The similar thing holds for everything. So back in the RGB coordinate system, if you want to display a red looking color, you need to use the coordinates 1, 0, 0. This shows the presence of red, absence of green and blue. Back in the CMY color coordinates, you need to have the coordinates like 0, 1, 1, which means that that's the presence of magenta and yellow. If you add it together, it absorbs everything except red, so red gets reflected. So CMYK color model. So why do we need to have it? I said that the CMY color model is mainly used for the printing purposes. It's a subtractive color model, and theoretically it's proven that cyan, magenta, and yellow, when you add these three things together, they subtract everything from the white light and it produces the dark image. So practically the dark image which is produced by mixing all these three colors are not pure black. So in order to have a pure black looking thing in the printed paper, you need to have a fourth color called key. The black key is named as key because when you put B for representing black, it coincides with a blue color. So to avoid that confusion, we have the letter K for the black ink. And it is also a subtractive color model. It's used in color printing. It is so-called subtractive because it subtracts the red, green, blue from the white light. The drawback of the CMY model is that even when you mix the portion of CMY all together, you will get only a darker shade of gray, but not black. So in this model, we overcome this using a separate black ink. So in order to have a very rich looking black color, you first use the CMY portion together to get a darker version of the gray, and then you use the black color on top of it, so you'll get a very dark looking black color. So screen angle, this is the most important thing. So the screen for each color is set at a different angle. This improves the print quality and reduces Moire patterns. See, if you do not do that, you'll encounter Moire patterns which will look clumsy on your image. The color mixing will not be proper on the printed paper. So in this GIF, you can see that the black roller is being kept at the last. So it is mainly used to highlight the images. So if you want to have a red looking color that should be very rich in its shade, so you use the black color on top of the red. So for that purpose, you're using the black roller at the end. The similar thing holds for the digital color printers. So you can see the angle for cyan, magenta, and yellow. If the paper is inserted at 15 degrees through the cyan roller, then for the magenta it should be 75, for yellow it should be 0, for key it should be 45. From this you can observe that the cyan, magenta, and key should have a difference of 30 degrees. The yellow can be at 0 degree or it can be at 90 degree. This will reduce the Moire patterns. So now let's see how it is being converted to RGB color model. The textbooks, you can see that we have seen before in the HSV color model, in the conversion to RGB, you can see that R is equal to 1 minus C. So the same thing holds in this case also, but you have an extra element called key, which is the black. So what you're going to do is, when you transfer from RGB to HSV, you'll just use the maximum of RGB values as the key value, and then you will subtract from the CMY. You'll get the final result. The similar thing holds for CMY to RGB conversion as well. But in this case, you will take the minimum value of RGB and then you will subtract from the CMY elements. So in order to have a highly good looking color on the paper which is being printed by the printer, you can have your own conversions, adjustments. So this is one type of conversion. You can see that the red, green, blue, which is expressed in the range 0 to 255. So when you plug in the cyan, magenta, yellow, black values in this equation, you'll get the conversion from CMYK to RGB. So HSV color model. So this is invented back in the 1970s by the computer graphics engineers, especially for choosing the colors for the graphic design. This HSV, H stands for hue, S stands for saturation, V stands for value. This color model describes colors in terms of their shades and their brightness. It is a hexagonal cone representation of points in an RGB color model. The base of the hexagonal cone is obtained from the RGB color cube. You just place the RGB cube such that its grayscale is strictly perpendicular to the ground surface, and then you will have a top view of this cube. The image is being put at the bottom of this hexagonal cone, and then you will form the cone by having the darker shades of the color when going down the cube, going down the cone. So let's see how we are going to generate tones, tints, and shades in this. So here's nothing but it describes the color. You can pick the color by specifying the hue. Consider in this diagram, if the hue value is 0, it picks the red color. When hue value is 120, it picks the green color. So for getting the different shades, by fixing the hue value at a particular color, and then you will have the saturation at 1, which means that the image is not saturated, the color is original, and then you will adjust the value of V, which is the value from 0 to 1, to get the different shades of that color. So in order to get the tints, you'll do the same process by fixing the hue at a particular color which you need, and then you will fix the value V, which is 1, so the image will be pure, it does not have any black color mixed with it, and then you'll adjust the saturation from 0 to 1. So you'll get the different tints by this process. So if you wish to get different tones of this color, you'll just do the same process by fixing the hue at a particular color which you need different tones, and then you will adjust the value of saturation and value in the range of 0 to 1 to get the different tones. So back in this cross-sectional view of the hexagonal cone, you can see the shades which are obtained by adjusting the value from 0 to 1, and you can see the tints over here which are obtained by adjusting the value of saturation from 0 to 1, and the entire surface here is the tones which can be obtained by adjusting both the saturation and value from 0 to 1. So let's see the process of conversion of HSV to RGB. So first you need to know that the H is expressed in the range 0 to 360, S is expressed in the range 0 to 1, and the V is expressed in the range 0 to 1 as well. So in order to do so, you will first calculate the three parameters C, X, M from this H, S, V values by simply plugging in this equation. Then you will find the R dash, G dash, B dash with respect to the hue, angle, and then with the obtained R dash, G dash, B dash value, you will calculate the RGB by simply plugging these values in this equation. You will just simply multiply this R dash with M. You will add the R dash with M, and then you will multiply by 255. Similarly, you will do it for G and B. The 255 means that the RGB values are expressed in the range 0 to 255. In that way, you can get different shades of RGB, different shades of color, or you can get more colors by expressing in 0 to 255. Next, you can see the conversion of HSV from RGB. In this process, you will first calculate the R dash, G dash, B dash from the RGB value by simply dividing it by 255, assuming that the RGB values are in the range 0 to 255. And then you will calculate the Cmax and Cmin from this calculated R dash, G dash, B dash value. You'll find the delta by doing the difference of Cmax and Cmin. So with the obtained value of Cmax, Cmin, delta, you just calculate the hue. The delta value is equal to 0. Then all the RGB are in the grayscale, so the hue value will be 0. And then with the value of Cmax, you calculate the hue value in this equation. For calculating the saturation, we'll just look at the Cmax. When the Cmax is equal to 0, then you know that the saturation value will be 0, which means all colors are same, which is in the grayscale. When the Cmax is not equal to 0, you will have this equation to find the saturation. The value is always constant, which depends only on the Cmax value. Whatever the Cmax, which is the value. Now let's look about the HSL color model. The HSL color model is simply like the HSV color model. It was used by the Tektronix Corporation. It was designed in 1970s, mainly for the computer graphics applications. In this, you can generate even more colors compared to the HSV color model. In this, the value parameter back in the HSV is being replaced by lightness parameter in this HSL. So when you have 0.5 of lightness, you have lightness with full saturation and a particular hue, you will get the pure color on that particular hue. So when you increase the lightness beyond 0.5, you will get the lighter version of the color. When the lightness is at 1, you will get the pure white. When the lightness is at 0, you will get the pure black. Likewise, when the saturation is at 0, you will get white. When the saturation is white or gray, when the saturation is at 1, you will get the pure color. And I forgot to tell, this color model, the representation is done by two cones. Let's look at the parameters of HSL model. You got the hue here, which is expressed in the range 0 to 360, starting at blue at the 0 degree. Saturation is expressed in the range 0 to 1, which means 0 is at grayscale, 1 is the primary color itself. The lightness, it is expressed in the range 0 to 1, where 0 is the black, 0.5 is the primary color itself, and 1 is the white. It's over here. Now let's look at the applications of HSV and HSL color model. It is used in color selection tools. It's the main purpose. It's why it is being invented. It is used in computer vision. It is used in image analysis for feature detection. It is used in robot vision for object recognition. It is used in image editing softwares. It is used in the analysis of medical images. It plays a vital role in all these fields. And that's the end of our presentation. Thanks for your kind patience. Thanks for your listening. Thank you so much.